Welcome to Programming in Modern C++. We have been discussing certain complementary and supplementary content in tutorials. Particularly from tutorial 1, we started discussing about how to efficiently build a C or C++ project. We have made specific reference to the build pipeline of GCC, though other compilers can also be used in a similar way. We understood the differences between source and header files, what to write where, and initially we took a deep look into how C preprocessor CPP can manage the code during the build. We talked about different dialects of C, C++, standard libraries, and we have seen that if we are doing the build manually, giving command one by one using GCC, then how can we build a project? In this tutorial 03, the third tutorial of the series, we are going to talk about a very interesting utility that GNU provides, and kind of it has become all pervasive in the build process everywhere in all kinds of software. May not be the specific utility, but utilities on the same principle. The GNU build utility is called make, how to make a C or C++ build file. It is popular, open source, and it performs dependency tracking build, and very good to know for any software developer. So, this removes the laborious, error prone and time consuming manual process by introducing a kind of automated scripting. So, we are going to discuss and understand about this make utility, and here is the outline of items which is also on the left bar. So, make utility, if you want to learn more about this, there are certain sources which are I find good. There is a given here linked. So, let us first recapitulate the example build process using a very simple project which has a it's basically the Hello World project, but written in a little bit more structured manner to introduce the basic concept of make. So, we have a hello.h which basically defines the header of the my hello function. Right? Then we have hello.c which is the implementation of hello.h, which for that my hello function provides the body, the implementation. And finally, we have the application file main.c which calls my hello as it finds in the hello.h header. So, application file, source file and header file, the three components of the project are here. And as you have learnt by now, this is we can build this in the current folder. The current folder is designated by dot. We can build this in the current folder by this GCC command, GCC -o, which says the target name is hello, and these are the two source files the translation units to build, and the include of the header hello.h will be available in the current folder. That is what this -i dot designates gcc command. We all have learnt and understood this well. Now, when we do this command, actually what happens are these, or rather I should mark only the first three, that it builds hello.c, creates the hello.o, builds main.c, creates main.o, and then links hello.o and main.o to build the final executable hello. Optionally, I could also when I actually give this command, it also actually what it does is main.o and hello.o that it has created, it will remove them from the folder as if they were temporary files. Okay. So, this is the basic manual process of build that you have already seen. Now, we are going to show you how to automate this process through scripting. Right. So, before we get into that utility, let us try to see why we at all need this kind of a utility. There are several reasons, and the most important ones I have listed here. The first reason is volume. The typical projects, we are now doing just in course academic projects 2, 3, 4 files, but a typical projects have hundreds of folders, source files, header files, and they need hundreds of commands. So, it is time taking to type those commands, and if we have to do so much of typing, it is not only the time, but it is going to be error prone. So, handling volume is a major motivation for going for scripting. Second is the workload. See, it is not that I have created a project and I build it only once. I will be building it several times repeatedly, even within a day, because as I add code, as I correct code, as I run and see that things are not as I wanted, as I debug. So, repeated builds are a regular requirement. So, it is not only the volume of task, also the overall workload is really, I mean, it might actually be more time taking and laborious than the actual coding and fixing problem. The third is, often there are dependencies between these builds that we do of the translation unit. What do we mean by dependency? Say for example, in the project we are seeing, suppose we have made some changes only in the hello.c. If we have only changed hello.c, we just need to build hello.c into hello.o, not main.c again, assuming that we have not removed the .o files after the last build. So, we just need to, if the change only hello.c, then we do not need to execute this command. Similarly, if we have changed only main.c, we do not need to build this hello.c into hello.o. However, if this is if changes have happened in the source files, but what if I have made a change on the header file? Now, this header file, as we have seen, is included both in hello.c as well as in main.c. So, if I have made some change in the hello.h, then I will actually need to build both of them, right. So, there is a decision to be made in terms of what file or which files have been changed, and based on that which translation units need to be rebuilt and what linking needs to be done and so on and so forth, and that is what is known as the dependency. Dependency says that if I change a file, then what are the files that have already been built in .o or say even in other .i, .s if we are doing any other files that will get affected by the change in the header or source file that I have made. So, managing that, remembering that itself would be a very difficult problem if the project is large. Then there is a question of diversity. There could be different build tools. I might use some specific libraries which may require a different set of tools, different flags, different folder structures and so on. So, there is a diversity in the project. In a large project, it is not as flat as just having 3 files in the current folder, right. So, all of these we need to be managed in an automated manner, so that it is efficient, it is easy to make it correct, it is easy to repeat that, and we can always kind of compute what is the optimal amount of task that we need to do by analyzing the dependency and just build that much. So, GNU Make is such a tool. Here is an interesting cartoon which refers to the historical origin of makefile or make utility, though exactly the make that we use today is somewhat different. Make was originally created by Stuart Feldman in April 1976. So, that is nearly 50 years back, and it was done in Bell Labs. So, what motivated Stuart Feldman to go for such a utility is his friend Steve Johnson. So, Steve Johnson was a very gifted programmer, and he was working on some complex project, and he was exasperated and came to Stuart and said that, Stuart, I have been working since morning trying to debug a program, and I wasted my whole morning because the file that I compiled is not the correct one. So, with that compile, my actual cc start.o, cc is another form of compiler, GCC kind compiler, dot object files were not properly updated, and therefore, I wasted all that time. So, this is the kind of problem. So, Stuart felt that why do we have to do this manually, why can't we automate this process, and that gave birth to the make utility. So, how does a make file look like? The anatomy of a file, it is somewhat like this, that there are what is known as targets. Target is something which you want to create by doing the make, and there could be multiple targets. So, here when we write something within square bracket, it means that it is optional. I may have it once or I may not have it at all. So, the target, so there has to be at least one target, that is why the first target does not have the bracket, but there could be multiple targets. Then there is a colon separator, which is very important, and then we have 0 or more components, right. So, it says that if I have the target to build this particular file, then what are the components that participate into it, or in other words, what are the components whose change would trigger me to rebuild, remake this target. So, that kind of gives you kind of the dependency information or the input output information. Then the question is, how do I actually do the make, or how do I actually do the build? So, for that we give commands. Again, there could be, I mean, in some cases there may not be a command and there could be multiple, but every command must be within one line and it must start with a tab. This is very, very important in the syntax of the make utility. If you just give space, it might look the same, but it will not work. You will get very weird kind of errors. So, always make sure that the first line, first character of the command must be a tab. So, use the tab key to provide that, and there could be multiple commands to this. Right. So, this is the basic anatomy. You could look at it in the code details as like this. So, here is the target, here are the components. I have two components here, and here is my command, and what you cannot see, but has to be actually a tab, not just spaces. And I have made some pointers for the file names. So, these text files, tiny make files will also be available to you for practice. Right. So, we write this. So, if we put this command into a file which name is makefile or makefile with a capital N, and then run the command make, then it will execute that command. So, what it will do? It will take the target hello, and this is the only target given. So, it takes that target and executes this command. This is the simple. Now, there are obviously several questions. First of all, if I write my commands into a text file called makefile or capital M makefile, then I can just do make. But if I use something like this that I have written here, then how do I tell that make according to that file? So, I can do that by putting -f and then giving the name of the file. We will come to those options later on. The other question certainly is here we are talking about a very simple makefile which has only one target. What if I have multiple such targets in the same makefile? Which one do I build? So, there are ways of doing that, there are ways of specifying that as well. So, makefile in general comprises a number of rules. So, these are my rules: target, components and command followed by the tab. Hash in a makefile means a comment from that point till the end of the line. Right. So, there has to be a tag, we have already seen, and hash is for the command. These details are noted here. Right. So, that is the basic structure of a makefile. We say the anatomy of the makefile. So, if I look at the anatomy in little bit more detail, we will see that here is a target, here is a command, and you have some more stuff here which is kind of variables, and we will see what variables are and why they are important. And as you can see here, there are multiple targets. So, you can, if you just do make, it always does the target which is named all, that is a given name. For other targets, you can give your own name. So, what all says? All says that to make all, I need test. Now, test here in this case, in general it could be any file, but in this case the test is another target. So, all will make sure that you do this particular build command. Right. So, there could be several variants of that, we will slowly come to all that. Now, what happens is, I mean you may want to retain this, or you may want to skip this also. That is what actually happens internally is based on the target and the components. There is a dependency graph, because every target depends on the components. So, there is a dependency graph, and that has to be, that dependency graph must be a cyclic. It cannot be, cannot have a cycle, but because then you will not be able to make that. So, that is through the rule syntax, it converts into a semantic graph, and that itself is the makefile. This is what we are doing for creating the makefile, which we are going to learn. Then there is a analyzer for the make, which decides on the target, the prerequisites, the components and the command. Those are created in the analyzer. Then there is a make processor. There is another make compiler, which compiles the make script. Make is becoming a language. So, there will be a compiler for that, which is called the make processor, which actually takes the build command, and from the build that has been done, it generates the actual commands on your command prompt or the shell prompt. So, that is the overall flow of the make architecture that you will have. Now, there could be variables here. For example, you will find in this, we can write CC colon equal to GCC, which means CC is a simple variable. So, wherever I write CC within dollar parenthesis, it will actually mean this variable. Right. Similarly, C flags is another variable, which I have written as equal to minus I dot. There is a subtlety here. You will find that in this case I have written it as colon equal to, which says that C c is a simple variable, and here I have written it without the colon, which says that C flags is a recursive variable. We will just immediately discuss what they mean. A simple variable is expanded as soon as it is encountered, right. So, this example is illustrative. I write a variable make expand do colon equal to, which means that I am doing a simple variable. So, which means that if I do $cc minus m is the meaning of this variable. So, wherever I will use this variable, and every variable is to be used by a within a dollar, right. So, as I do $make depend, then dollar will expand to whatever it would be. So, here is the recursive one. The difference in the recursive one is that it is lazy in evaluation. So, what do I mean by that? Look at it here very carefully. Here, while I am doing make depend, I am saying that make depend is whatever $cc is followed by minus m. So, it is referring to another variable. Incidentally, that variable is not been defined as yet, that variable happens later. The definition of that variable happens later. I do the similar thing here, and also the variable depends later. Now, what happens if it is a simple variable? As soon as the definition of that variable comes, as soon as this comes, it is evaluated. So, what is $cc? Cc has not been defined. So, make by default assumes that it is a blank space. So, it expands it to a space, then minus m, minus m. But when I have it as lazy, as a recursive definition, by virtue of not having the colon here, then it does not immediately expand $cc. It just remembers this is. So, when later on it finds the definition for Cc, and after that when it actually has to do make depend, at that time it goes back to that definition and start evaluating. So, this goes back now here. By this time it has found Cc. So, it knows Cc is GCC. So, it takes and puts GCC here and expands to GCC minus m. So, in a simple variable, whenever you encounter, you evaluate. In terms of a recursive variable, you remember the definition and you evaluate only when you are going to use it, only when you are going to expand it, right. So, in between this, if certain missing variables have been defined, then they will be properly used. So, that is the basic difference between these two. So, if I have to use only simple variable, then in this case I have to put Cc equal to GCC before I put make depend equal to $cc minus m. But if I use recursive variable, then I can put them in any order, but obviously before I try to evaluate make depend, right. So, this is this is the way I can have variables, and variables basically make it easy to write. For example, I am saying Cc is a variable defined as GCC. How does it help? Wherever I have to write this compiler name, I will put this. So, later on if I decide no, I do not want GCC here, I want G++ here, or I want CC here. CC is another Linux compiler which is very has been widely used as well. I do not have to go and make changes at every point. I just have to change the definition here. So, in a way, I mean, if you think in terms of principles, in terms of philosophy, you can say that this is like doing a hash define. We are hash defining symbols. Why? Because that symbol is used at multiple places, and instead of having to change it everywhere, I can make changes only at once. So, and also naturally using variables make it easier to read the code, makes it easier for me to put commands and understand what I am doing and so on. So, here I have two variables, both recursive, and then I have another third variable which say what is the dependency, that is what is the name of the header file on which the build depends, and then I write a rule like this. Just to understand, just look at the rule. Left hand side is the target. So, what am I saying is the target? I am saying that the target is %.o. What does percentage mean? Percentage means any string which will match here, if it is followed by .o. So, any name of any file which has .o extension will match the target. So, I am saying, so in other words I am saying that to build a .o file, you have to make use of the dependency on the right. What are the components? The first component is %.c. That is whatever you have taken as .o file name, say hello.o, then by the same name you will have a component called hello.c. If I do main, if I have found also main.o, then I have a main.c, right. So, this is the first component, and the second I say it depends on $deps, that is what is deps? I say it is depends on hello.h, because that is what I have defined as the variable. Now, the advantage of saying doing this is, if I do not do this, then I will have to write one rule for hello.o, another rule for main.o. If there are 20 translation units, then I will have 20 rules, but all of them will have some kind of some .c producing .o and a set of files on which it is dependent. So, by this single simple rule, I am able to capture the entire process of source files being compiled into object files as a proper target dependency requirement. Now, what is the command? The command to build is cc is my compiler, whatever I will put here will come here automatically. Then I say it is -c. So, we am saying that you generate the .o file, right. Now, I am saying what is the mine, and I have this flag which says that the flag says -i dot, which says that anything that I include will come from the same folder, right. Now, the question is what is the input and what is the output? What do I need? I need, if my target is hello.o, then my dependency source has to be hello.c. If my target is main.o, my dependency target must be dependency must be on main.c. So, I say that by these special make symbols which say $@, $@ means the left hand side of the colon, that is the target, and $< means the first component, right. So, if I have to make hello.o, which is coming from $@, similarly if I have to make main.o, I have to come from, that will have to come from the $@. Now, so then this process in a very compact way I can define the multiple rules into one simple rule. I do not need, because all these are structures are the same, only thing different is what is the .c file name, what is the .o file name, and that is where these these potential make symbols or make language instructions will take in place. And then I write another rule which says that my target is hello, which is the final executable, and these are my components. It depends on the .o files, and this is my command. Right. So, this is a simple process that will be involved in putting the dependency together. So, if we want to extend that, we have this we have seen. We can also want to make the obj files into a set of dependency. So, with that, this is same. Also, the last line I make it compact. I do not list hello.o, main.o like that. Those are all listed at one point, and I can just use them as $obj. Again, I use the $@ to mean the left hand side, and these are, there will be multiple of them. So, $hat are the names on the right hand side, all of them will be expanded in here. So, this is how the make can actually work. I am sure you have got a sense of this. So, let us take a little bit of example to understand more. So, what I do is we will assume a certain source organization. In a big project, you will not put everything in a single source file, in a single folder. Rather, you will have different folders having different types of files, bin for executable, that is binary, inc for include, lib for library files, we will see what they are, obj for object files, src for source files, and so on. So, let us look at this simple code tree. This is my home project, wherever you can put it. Then I have a application binary folder which will have my exe finally. This is my include folder. This is if I have some libraries. We still are not talking about libraries, we will talk in the next tutorial. We have the object files in obj, source files, and in the root, that is in the home, I have my makefile. So, all that I need to do is to go to my home and do make, and that should build my entire project, right, and put the files accordingly. So, that is what I do here. This is my command, and I define different symbols for my folders. Why do I do that? Because somebody might want to call the include directory as inc, somebody might want to call it include, all these different names. So, I can just change it here, so that I do not need to change it anywhere subsequently. I have my flags, and then I use a set of macros to actually use these variable names and create the actual expanded name. So, all that we are saying, that pattern substitute, what do we substitute? $idr, what is $idr is inc slash percentage. What is slash percentage? Slash is obviously separator, percentage is whatever comes from the dependency. So, whatever is the dependency underscore dependency as hello.h. So, this will give me a string which is inc slash hello.h. Similarly, I do that for sdir with src as source, which has two source files. So, it gives me src slash hello.c, src slash main.c, like this, right, very standard way of writing. Do not have to remember this form, you can always look up the syntax or copy paste from here. Then my rule becomes very simple with this structure also. My object files will be in odir, object dir slash %.o, we have already seen that, dependent on the source files and the dependencies, very nice. Here you see a alternate syntax, I have put a semicolon. Normally, I have to put the rule in the next line after the tab, but we can put it right after the components by giving a semicolon, and here is my command. You have already understood what these symbols are. They one by one will take the .o and the .c and create, so expand into so many commands. Similarly, I can have it for the binary file rule, the binary folder, the obj object has to be, it must depend on the object files and the command for that, and so on. It is very typical that you might want to also have a clean target. The clean target is if you have got all your different folders are getting different files generated, and so what if you want to erase everything and start afresh, or then you can do a clean one. So, which is say in Windows it will be del object directory is cleaned, binary directory is cleaned, or rm-f in Unix, which will do the same thing. Now, since clean is not actually a file, it is not a file, right. Normally targets have to be a file which you generate. So, you have a very typical, very interesting exception given in make, where you say that this target is .phony. .phony is known as .phony, and you put whatever name on the dependency, and that is treated as if it is a file, and you can build with that file. Right. So, this is what the whole structure is. So, the make command is now simple, it has make, then optionally you can specify the file name -f. You can give different options for doing, for example, you can ask it to be verbose, you can ask it to actually print whatever it is doing, and then you put the target that you want to build. So, if you just do this without giving anything, it will do the basic routine stuff. Otherwise, you can say my target is to build hello.o, or my target is to build main.o. So, you can put anything which is on the left hand side in the target, put that, or you say that my target is to do a clean, I want to remove everything. And if I do not give a target, then it does all according to the dependency, it does .os, then it will do different .os and then link them to the final executable. Right. So, that is the basic process. There are other options, like you can set the directory, you can put the make debugging information, you can have include directory and so on. So, all these are listed here, and if your one make command is too long, you can continue it with a backslash and go to the next line. We had talked about this in the CPP also. So, it is exactly the same type of functionality that you have here. There are a variety of make naturally available. There are different, and though make we are discussing in terms of building projects, is not limited to building projects. It can also be used to build any kind of package, or can be used for building installing something, uninstall. It is kind of a process to automate what goes on in the system, where you have certain conditional things to be written. So, the dependency is basically like writing if else in a different way in the build world, right. And do not think that make is there only for C++, though that is very common, but it is available for any language whatsoever, and there are a variety of make utilities which are available. We are going to use the GNU make, but there is make for Windows, earlier known as there is one from Microsoft called NMake and so on. Chrome specifically has a different one, and so forth. So, we have in this series of the third tutorial, we have learnt about the make utility, which is a popular free open source dependency tracking builder tool, and which can help you really automate your build process and make it efficient. And small examples as I have given, and the make files also, I would request you to just start using them and get familiar with it. And the syntax is not a very syntax friendly language, right. Some peculiar $@ and so on. So, you do not really need to remember everything, have a kind of a sample makefile with you, and wherever you need you can edit it appropriately and create your respective makefile. I hope this tutorial will really help you and take you ahead in the automated build process, and see you in the next tutorial when we will close about the C++ build processes.